Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here today because, well, we're going to unpack one of the most fascinating and totally invisible forces shaping our everyday lives. Think about the last time you were at the grocery store, or maybe browsing online, and an eerily accurate recommendation popped up. You know the feeling, right? It almost makes you wonder if your phone is actually listening to you. Well, today, we are going to decode exactly how that happens by exploring the brilliant logic of association rule mining and the famous a priori algorithm.
Let's start with a scenario we literally all know. Have you ever wondered why bread and milk are, always bought together? Or, more importantly, how retail systems instinctively just know exactly what items we're going to want to buy at the same time? Honestly, it feels a bit like magic. Or, again, like they're secretly listening to us. But I promise you, it's definitely not magic. It is pure, elegant mathematics. And that's exactly the everyday mystery we're about to solve right now.
Okay, let's dive into this. Here's our roadmap for today. We'll start off by decoding the shopping basket. Then we'll break down the math behind the rules. After that, we'll explore the a priori algorithm explained, weigh its strengths and limitations, and finally, look at some pretty mind-blowing real-world applications.
Let's jump right into Section 1, decoding the shopping basket, and ask what exactly is association rule mining. To understand these predictive shopping behaviors, we really have to look at the foundational concept driving them.
You know, what's really fascinating about association rule mining is both its history and just the absolute simplicity of the concept. It was introduced back in 1993 by Rakesh Agrawal, Tomasz Imieliński, and Arun Swami. Essentially, it's a data mining technique used to discover hidden relationships in massive datasets. Now notice, this is an unsupervised learning technique. That just means the algorithm isn't given a specific target to predict. It doesn't actually know what it's looking for in advance. It's kind of like letting a detective walk into a room without telling them what crime was committed. They just look for the clues that naturally group together. It sifts through mountains of data to extract highly logical if-then statements, like if you buy bread, then you buy milk. It simply discovers how items co-occur organically.
What makes this technique so incredibly efficient is how it views the world. It works best with categorical data, like items in a shopping basket. It completely skips complex feature scaling or continuous numerical data. Instead, it just uses simple transaction lists or a binary matrix. A 1 means an item is present in your basket, and a 0 means it's absent. It totally doesn't care if you bought 2 loaves of bread or 10. It just asks a simple binary question. Is bread in the basket? Yes or no? If an item is missing, it's just a 0. And this simple 1 and 0 approach is a real game changer because it allows the algorithm to effortlessly process large, sparse datasets containing literally thousands of possible items.
And that brings us to Section 2, the math behind the rules, specifically support, confidence, and lift. Don't worry, we're going to keep this super clear and stick with a simple grocery example. There are basically 3 core probability metrics that act as the engine for this algorithm.
Let's start with this first number, 0.4. Imagine we have a dataset of exactly 1,000 grocery store transactions. If bread and milk are bought together in 400 of those 1,000 transactions, the math is totally straightforward. 400 divided by 1,000 gives us 0.4, or a 40% rate.
So that 40% represents our first major metric, which is called support. Support measures exactly how frequently a specific item set occurs in the complete dataset. And why is this so vital? Well, in data science, you absolutely want to eliminate statistical flukes. If someone buys hot sauce, a single banana, and a pair of socks exactly once, we obviously don't want to build a whole business strategy around that one weird transaction. Support acts as a crucial initial filter. By setting a minimum support threshold, we weed out all that rare, random noise and keep only the frequent, meaningful patterns.
Now, let's look at another number, 0.8. Sticking with our example, let's say that out of the entire dataset, there are 500 total transactions that contain bread. And, as we just established, 400 of those also contain milk. If we divide those 400 milk and bread baskets by the 500 total bread baskets, we get 0.8, or a massive 80%.
This 80% represents our second metric, confidence. Confidence measures how reliably the consequent, in this case, milk, occurs when the antecedent, bread, occurs. Essentially, it tells us that 80% of the time someone puts bread in their basket, milk goes in there too. It's an amazing measure of reliability for our if-then rule. However, high confidence alone can actually be a little misleading. Think about it. What if milk is just universally popular? What if literally everyone buys milk, regardless of whether they bought bread or not?
We need a way to prove that the relationship isn't just a coincidence.
And this brilliantly illustrates our third metric, lift. Lift steps in to compare the actual observed occurrence of bread and milk together against what we would expect if they were completely statistically independent of each other. If your lift is greater than 1, you have a positive association. The items are truly linked. A lift of 2, for example, means they occur together twice as frequently as we'd expect by random chance. If lift equals 1, well, they're independent. And if lift is less than 1, they actually have a negative association, meaning buying one makes you less likely to buy the other. Lift is basically the ultimate lie detector for our data. It proves that the relationship we're seeing is actually real.
Now that we've got a handle on the math, let's move to Section 3, the a priori algorithm explained, and see exactly how the engine works to process all this math and find our rules.
At the very heart of this technique is the a priori principle. This principle simply states that if an item set is frequent, all of its non-empty subsets must also be frequent. Think of it like this. If buying an apple, a banana, and a carrot together is a frequent pattern, then just buying an apple and a banana together absolutely must also be a frequent pattern. This simple piece of logic is a genius shortcut. It saves the computer from having to calculate the math for every single impossible combination in a massive real-world grocery store.
So let's walk through the algorithm step-by-step process. Honestly, it acts very much like a sieve. First, it loads the data, and you set your minimum thresholds. Second, it finds one item sets. It scans all the single items and literally just throws away anything that falls below your minimum support threshold. Third is iterative joining. Now this is where the magic happens. It combines surviving items into pairs, checks their support, and throws away the rare ones. Then it builds momentum, making combinations of 3, then 4, and repeating this until no larger item sets can be forked. Fourth is rule generation, where it creates those if-then rules from the survivors. And finally, step 5, it filters and outputs, calculating the confidence and lift, discarding anything weak, and presenting you with only the absolute best, most powerful rules.
But of course, there's always a catch, which brings us to Section 4, Strengths and Limitations. As amazing as this is, we have to honestly evaluate the reality of using it. Why is this technique so beloved by data scientists, but also where does it really struggle? When we weigh the pros and cons of this algorithm, a pretty clear picture emerges. On the strength side, this algorithm processes huge transactional datasets and gives us results that don't require a PhD to understand. A simple if-then rule is highly interpretable for any business owner. But look at the limitations. As the number of possible item combinations grows, evaluating millions of combinations takes immense processing power, making it computationally expensive. It can also spit out a massive number of redundant or just completely uninteresting rules. So, the crucial point is, we must always remember, correlation is not causation. Just because two things are bought together statistically, it definitely does not mean buying one causes you to buy the other. We're looking at statistical relationships here, not causal explanations.
Let's move into Section 5, Real-World Applications Beyond the Grocery Store. We've talked a lot about groceries today, but this exact same logic scales up to solve massive, real-world problems far beyond a simple trip to the store.
Just look at the astonishing versatility of this algorithm. Yes, it drives market basket analysis and those online product recommendations we all see. But it's not just retail. In healthcare, doctors use these exact same if-then rules to spot hidden links between patient characteristics, symptoms, and diseases. Meanwhile, over in the finance sector, institutions use association patterns to flag highly unusual transaction combinations, which is huge for detecting fraud. In web usage mining, it reveals how users navigate complex websites. Even in education, it helps analyze relationships between course selections, student activities, and academic outcomes. It's the exact same math discovering unknown knowledge across completely different fields.
Which leaves us with a fascinating final thought. From the food in your fridge to the pages you browse and the transactions on your credit card, you are constantly generating data. And as we've seen today with the a priori algorithm, that data follows highly predictable rules. So I want to leave you with this question. What invisible patterns are hiding in your everyday data footprint? Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.